Good morning. Welcome back to EELE 461-561 Digital Systems Design. This is Brock. This lecture corresponds to our Wednesday meeting on April 22nd. And in this video, we are going to, let's see here, get this out of here. Go away. So in this video, we're going to look at differential terminations, okay? So remember, a termination is a resistor network that we put at the end of a transmission line or at the beginning of a transmission line, and we try to match the impedance to the transmission line itself such that there are no reflections. Okay, and it's pretty simple. When you have a single-ended line, you just put a resistor with the same impedance at the end. And same thing with source termination. You just put the same. You got a 50 ohm line, put a 50 ohm source termination resistor, and life is good. But now we have a situation where we have two lines that are transmitting our logic value, and they are driven differentially. And what we've learned is that there is different impedances depending on how the lines are driven. And initially you'd think, well, aren't we just driving the odd mode? You know, the two lines are always complementary to each other. But the trick is that, no, we're not always driving the odd mode because we have a common mode that is common to both P and N. And that common node can be noise that's a transient that's injected on both nodes, and it'll travel down. And if it doesn't have a termination, it'll bang around on our transmission lines. And so we want to be able to terminate ultimately both the the odd mode and even mode, but we got to start changing our terminology because odd and even mode has to do with one line. So we're no longer looking at one line, we're looking at two lines. So we're going to kind of walk through this and ultimately get to a couple different networks that you can use on differential pairs in order to terminate both the even and the odd mode, or said another way, the differential mode and the common mode. Okay, so let's look at what characteristic impedance is versus the differential impedance. Impedance is always V over I. No matter what anybody tells you, that's law. Okay, but Z naught is defined as the V over I of a single line. Okay, and that's where everybody else held at 0. When you think about the differential impedance, it's still V over I, except it's V diff over I diff. And remember, V diff is P minus N, so it's the voltage between the two nodes. But I diff is the current that flows into and out of into P and out of N. Well, guess what? If they're opposite voltage polarities, you have the same current going into P as you do coming out of N. And so actually the I diff stays the same. And so what ends up happening is if you tried to compare Z naught to Z diff for uncoupled lines, let's say these two were far away from each other, but you still drove them differentially, what you'd see is that your V diff is twice the single-ended voltage, which is what we expect for a differential voltage, you know, P minus N, but the current's the same. So it's kind of strange, but that's just reality. So when you define the differential impedance of what does this look like, what is V diff over I diff, it turns out that related to the single-ended characteristic impedance for an uncoupled line, V diff is equal to 2 times Z naught. Okay, that's interesting. That means they're not coupled, so that's kind of interesting, but that's cool. We'll come back to that, though, because that's going to allow us to pretty simply terminate an uncoupled differential pair. What about Z common? Let's relate the common impedance to Z naught. So what is Z common? Well, Z common is the impedance of both trace 1 and both trace 2 to ground. Because remember, these are at the same voltage potential, so it's almost like having them shorted together. But if you think about what V common looks like with respect to Z naught, you know, Z naught is basically these lines to ground. So Z naught to ground, Z naught to ground. So if you were assuming that these two traces were at the same voltage, the V common, well, what it looks like when you look to ground through both of them is Z naught in parallel with Z naught. So the common mode impedance is actually 1/2 Z naught. Okay, not a big deal. These are just two new terms. We have Z diff and Z common, and that's how they're related to Z naught. Now this is for the uncoupled case, okay, but that's fine, okay, with whatever. All right, so let's now think about this. Let's remind ourselves what we're doing. We've got Z diff is equal to 2 times Z naught, Z common is equal to 1/2 Z naught, and that is for uncoupled. All right. Now let's try to start thinking about the modes, right? So in the beginning we said we're gonna have a differential mode, we're gonna have a common mode, and then we have this single trace mode. Differential mode was what we defined for Z odd, but it was looking at one trace while the other was a victim or a neighbor that was messing around with us. Now our neighbor is not messing around with us. Now our neighbor has moved in with us. So we are two people living together. We are two butts in one underwear. We work together. And so this odd mode from before is now what we call a differential mode. And we care about the way that these modes work as a continuous wave. Same thing with common. We used to call common the even mode. But remember, even mode was with respect to one line while its neighbor was messing around. But now the neighbor is part of us. So we have the common mode represents what these two traces look like when they're both driving the same way. Now, of course, this is the signaling. This is like DC offset or noise. So differential is the differential wave, which is what we think of. Common is just DC offset or common noise. Single trace, what does this mean? Here's what this means. This is no longer part of our life. Okay, we no longer will ever allow this to occur because we are going to drive these either differentially or commonly. We'll never have a situation where we take one of them and just drop it to zero for no reason. So this is out of our life. Okay, so we only have two modes in differential. All right, now what happens if these couple? So we already defined what it looks like if they're not coupled. So Z diff is 2 times Z naught. Well, you know what? If we bring these together, all that changes in terms of like the difference between Z naught and what we call Z odd is that they're coupled, right? But it's the same thing. So we can extend that and basically say if there's coupling between these, meaning that we just brought the traces really close together, then Z diff could be defined as 2 Z odd. So these two equations are kind of the simplest way to come up with Z diff. And one is for no coupling, so the lines are really far apart, and one is for there is coupling, which they're really together. And this is an important concept because you can use differential signaling without having coupling between the traces. You can absolutely do that. Okay, what about even? Same thing. Z common is 1/2 Z naught if there's no coupling. Well, when you drive both of them the same way, you have that same relationship as Z even to Z naught, which is where Z even is just when they're coupled and you still drive them the same way. So Z common is 1/2 Z even, okay, if there's coupling. So these two are valid. How would we terminate this? Well, we remember at the beginning we had this, oh my gosh, well, what does a single line look like when its neighbor's messing around with it? Z naught is some value. It's got Z odd and Z even. First and foremost, we don't have Z naught anymore. We only have Z diff and Z common, which are made up of Z odd and Z even. So we need to try to terminate both. So we are going to try to come up with some scheme to terminate a differential mode and also a common mode. So let's start with the differential mode, or we can call it the odd mode. So if this is the differential impedance between them, okay, so this is the impedance that you see, you could just put a resistor that's equal to 2 Z odd at the end, and that will terminate the wave. And that's it, okay? So think about that. If they're not coupled, you can put 2 times Z naught. If they're coupled, just put 2 times Z odd. And that will work. You will terminate the differential mode. And so this is really a common technique. It is very common to just say, if I have two 50 ohm transmission lines and I'm driving them differentially, just throw a 100 ohm resistor between them at the end. And that works for a lot of stuff. But it doesn't terminate the common mode. Okay? So if you got a blast of noise that was present on both of these and it propagated down to the end, there would be a reflection that came back. And so if you wanted to get like nutty, like you wanted to be perfect, you would terminate not only this mode, but also the case where you have like a blip on both of them that's common. So what does that look like? Okay. Well, let's see. So that's even. So here's the odd mode. What does it look like to terminate the even mode? Well, this one's really easy because common is with respect to ground. And so all you really do is you put Z even to ground at the end of both of these and you're done. And so when I say that Z common is equal to 1/2 Z even, The way that you implement that is putting Z even to ground at the end of both lines. Because then when the common voltage looks down, it sees this in parallel with this, that's 1/2 Z even. So once again, this is a simple termination to terminate the common mode. Here's the trick though. And if it was not coupled, you put Z not to ground on both of them. And that makes sense because that's what we do with single-ended. So here's the problem. You can't do both of these at the same time using those values I just gave you, or else they interact together. You don't just slap resistors on top of resistors and pretend that they act independently. They always interact with each other. So we have to come up with a way to terminate both. And it turns out there's two topologies called a pi termination and a T termination that you can use to accomplish both objectives. So let's start with the pi termination. You've got 3 resistors and R1 is across them, and then you label R2 twice because these are the same value. It's probably not technically accurate. This should be R2, R3, but these are the same values. So let's terminate the even mode. Remember, even as they're both happening at the same time. Well, when two things are at the same voltage, you come down here and there's no difference between this node and this node. So R1 actually goes away. So that is cool because if R1 is invisible to a voltage that's the same across both of these lines right here, the P and the N, then we can simply make R2 equal to Z even just like before. So that's fine. So we get to set the values of R2 immediately without having to worry about the interaction. But then here comes the interaction of, now we're trying to solve for R1, which is going to help terminate the differential mode. But when you think about the wave coming in here, you basically have current that goes through R2 this way and current that returns through the other R2, R3, this way. And so if you look at this, we need R1 to be in parallel with, or R1 is actually in parallel with 2 times R2. And if the way you think about that is if current is going into here, into this node right here that I have drawn as a ground, and it comes out of this terminal that looks like a ground, these two thingamajigs that I call ground, you can think of it as a short circuit. They're essentially acting as a short. So I have R1 in parallel with, here comes R2 plus R2. So you basically have 2 times R2 in parallel with R1, and that's trying to terminate Z diff. Okay, so I want Z diff equal to that. Rearrange, add in all the values, blah, 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 blah. And what you end up with is R1 is equal to 2 times Z even times Z odd over Z even minus Z odd. Okay, so when it all comes down to the end, here's what the pi network values are. 2 times Z even times Z odd over Z even minus Z odd, and then R2 is equal to Z even. Now, you can get this directly from line calc, and if you put that in there, this will work very well. And you could even drive this differentially and watch that there's no terminations. Then you could drive it commonly, so drive like a step on both of these going from 0 to 1 down here and see that there's no terminations. And from then on out, you have a perfect termination. T network is another way to do it. You have 2 R1 values that are the same, and then you have R2, and you just do the exact same, thing, you go through all the math, and it comes out to be, in this situation, R1 is equal to Z odd, and then R2 is equal to 1/2 Z even minus Z odd. And so in either case, you have these 2 networks which you can use to terminate differential pairs. Okay, so that is it. That's the theory of differential terminations, and that's it. We'll see you.